Good morning, all. So in today's class, we'll start with the truss problem. I'll explain the problem, what has been solved, and at the end, I'll give you a assignment problem, and you have to practice on that, so that you will come to know how you can work with these truss problems, design of truss problems. Okay. So we'll start. Okay. This is the problem what I have taken here, and it has been solved. So you need to design this truss members. Okay, so design the fan roof truss shown in the figure for the member forces given in the table. Use bolts of 16 mm diameter and of 4.6 grade. The steel is of Fe410 grade. Okay, so like this, you will be having the problem. It may be a fan roof truss, king post roof truss, a fink roof truss, anything. But our main intention is to design those member which are either under compression or tension. Okay, so that is the main this one objective of that problem over here. That is what you have to do in that. Okay, I have written some reaction here. Reaction at A and B are 80 kilonewton, and the uplift force is 30 kilonewton. We will come to this later. Okay, so this is the question what you will come across, and the truss what you see here. Okay, so this diagram will be provided to you, and you should be able to determine the length of each members. Okay, length means we require from one connection to another connection mainly. So that will be the length, unsupported length. Okay, so we'll be taking that itself as effective length here. Whatever lengths are mentioned here, so that themselves will be used as K into L, the effective length in the trusses. Okay, so what you have here is, what is the span of this truss? We can see here it is 9 meters. The rise or the height of the truss, okay, it is 2.6 meters. Other than that, the length of this member, principal rafter, okay, center to center distance between the connection is mentioned here, 1.73 meters center to center. Okay, so these are the member lengths what we have in this diagram. Other than this, we have these interior members over here. Okay, so we need to determine what will be the length of this member BE, CE, and DE. Okay, in the design, mainly when we are dealing with the design of compression member, the length of these members are required so that we can evaluate the effective length and determine the strength under compression. Okay, so these member lengths has been determined here. Okay, so what we have is, first is B. You can consider this triangle now. So this angle or pitch angle has been mentioned here, 30 degrees. Okay, if not, sometimes what you have to do is you have to calculate it from the available data. What we have is this rise is the central rise is 2.6 meter, and distance up to this middle, okay, half of the span, it comes out to be 4.5 meter. Total span is 9 meter, so you'll have 4.5 meter. Okay, in case if you don't have this angle mentioned in your question or not available to you in the diagram, okay, so in that case what I can do is I can consider this height and half the span of the truss and go for finding what is this pitch angle. Like that you can obtain the pitch angle. Okay, and whatever the length which are not available, okay, which will not be given to us. Okay, sometimes some length will be given, like this 1.73 is mentioned here on the principal rafter. Okay, and on the bottom time member these lengths of 3.3 meter, 3 meter, and also from this the overall length of the principal rafter, the total span of the truss can be arrived here. So they are given here. Okay, and another dimension what is given to us is the rise 2.6 meter. So if at all if you don't have the length of these interior members given to you, from the geometry of the truss you need to find them, you have to determine them. Say for example, now what we have is this particular height of this member C, this length of the member C is not available. So we can calculate it from the geometry of this truss. Okay, considering this triangle ACE. Okay, if I consider this ACE, this triangle, I can go for determining what is this height of this or the length of this member C. Similarly, B, if I want this length of the member B, then I can take this triangle over here. Okay, this angle is 90 degree. Okay, so it is not mentioned, but I assumed that this is how the question paper may come up. Okay, so sometimes you may have to judge it over here, or if it is correctly given, take the given data. Okay, and from this the length of this member can be determined. Okay, that is the length of B can be determined. Also what I require is length of this member DE. Okay, for that what I can do is I can consider this one triangle, one more triangle which will be there here, and then we can go for determining this length. Say I'll take this triangle. Okay, which triangle now D, E, and one more point over here up to the middle of the truss. Okay, from that what I can get, this blue line, this length is 2.6 meter, and E, and up to this point, up to the middle of truss, I know that the length is 1.5 meter. Okay, so 2.6, 1.5 meter. From that, I can get this length, hypotenuse. Okay, this length of the member D. Okay, so like this, you need to uh, determine the length which are not given to you or which are missing over here. Okay, so that length calculation will be like this, something like this. Okay, whenever required. So on that basis, here you'll find the length of all the members which have been determined or given to us. Okay, so for member AB, this is the principal rafter member on the principal rafter. Okay, this is one segment of the principal rafter here. So from the point A, okay, up to point B, the length is 1.73 meter. From center of this connection to center of this connection, the length is 1.73 meter. Okay, so that has been given in this table. AE, remember, it is 3 meters. BE, okay, so it is 2.45 meters, length of this member B. And the DE member, it is 3 meters. Okay, length of the member DE, it is given here 3 meter. And for CE, it is coming out to be, or it is given as 1.723 meter. Okay, so these are the lengths which have been given for these members of the truss. Along with this member length, what is given here is what are the forces, okay, that the member is subjected to. Okay, say first one, the member AB, this member along the principal rafter, it is subjected to a force of 27.5 kilonewton under compression and 24.9 kilonewton under tension. Okay, these are all factored. It is mentioned here, these are all factored forces what are given to us. Okay, so this member, when it is subjected to compressive force, the magnitude of force is 27.5. Okay, if at all if it comes under tension, then The magnitude of the force and tension, it is 24.9. On analysis, we'll come to know that. So considering wind from different direction, you'll come across these results. At some point of time, it will be experiencing compression. At some other times, it may be under tension. The magnitude of force, what it will be subjected to is this 27.5 kilonewton compression and 24.9 kilonewton tension. Similarly, for the other members also, the force to which they are subjected under compression and under tension are given in this table. Okay, so now we need to design these members for the forces what have been mentioned here. Okay, so normally what we'll do is we'll design for one of this force, okay, say for compression, and I'll check it for the tension, whether it is safe to take up the tension, the same member, whether it is safe under tension. Okay, so similarly, say here, if I come, the force of compression, even though if it is small, okay, 5.4, what happens is the length, what you find here, 2 meter and 3 meter, due to these lengths, the member may tend to buckle. So it is important that you check it for both the forces. Design it for one of the forces. Either you may decide the cross-sectional area based on tension or compression, but later on check it, okay, whether it is safe in tension and compression or no. Okay, that check has to be done. Design and check it. That should be done over here. So with this given data, okay, members, their length, the force to which they are subjected are there here with us. So, and also the grade of steel, it is 410, Fe 410 is the grade of steel, what will be adopted for this member. Okay, so that is the steel properties. Then what we have is bolts. It is told that to use bolts of 16 diameter and 4.6 grade. Okay, 4.6, it indicates ultimate strength is of 400 Newton per mm², and yield strength is 0.6 times 400, that is 240 Newton per mm². Okay, that is the grade of bolt. Fine, this is what we have. Now first job what has to be done here is go for determining the strength of the bolt. Okay, so here the details of the connections have been calculated. It is assumed that the gusset plate is of 10 thickness. Okay, so gusset plate thickness was not given to us in this problem. So what we'll do is we'll go for assuming the thickness of the gusset plate. So it is assumed to be 10 thick. And bolts, the pitch distance. What should be the pitch distance for the bolts? It is minimum pitch distance is 2.5 times the diameter of the bolt. Okay, so that comes out to be 40 End and edge distances, they are 1.7 times d naught. You have two criteria, 1.5 d naught, 1.7 d naught. Okay, so I have adopted 1.7 d naught, and the minimum end and edge distance, it is 30.6 Okay, so on these two, we'll finalize the pitch and end distance. What we are going to do is we'll provide a pitch distance of 50 and end and edge distance of 35 Okay, these are the connection details, or these are the distances in the connections what will be provided. The pitch distance between the bolts will be maintained 50 The end and edge distance with respect to the member, it will be maintained at a 35 distance. Okay, so that is the connection details. Now with that connection details, what we have to do is determine the strength of the bolt in single shear, double shear, and bearing. Okay, so from the clause you can get this strength, and it has calculated here. I have done this calculation for the strength of the bolt. So in single shear, VDSP, okay, so that comes out to be factor of safety, gamma MB for bolt. You have to assume, no, so for shop fabrication and field fabrication, it is 1.25 itself. Okay, so anyone you can assume that, and the value remains same for both. So VNSB, nominal shear capacity of the bolts, okay, it comes out to be 36.21 kilonewton. How this calculation is done? Here, I assume that all the shearing plane are lying in the threaded portion. No shearing plane is coming in the shank portion of the bolt. Okay, so in the threaded region, number of shearing plane 1. In the shank region, number of shearing plane 0. And the net area under shearing 0.78 times the gross area. It comes out as 156.8 mm². Okay, on substituting, what we get, the strength of the bolt under single shear, it will be 28.97 kilonewton. Okay, 28.97 kilonewton under single shear. Under double shear, what happens? It will be double of this, 2 into 28.97, which comes out to be 57.94 kilonewton. Okay, so when you use double angle section for this cord and the bottom tie member, bolts will be experiencing double shear. Okay, whenever you provide two angles back to back over the gusset plate, bolts will be subjected to double shear over there. Okay, and when it is case of single angle sections, they are experiencing single shear. Okay, so that's why both have been calculated here. And bearing capacity of the bolt. Okay, BDPB. So here BDPB, which is expressed in terms of VNPB and gamma MB, and VNPB in turn, it is 2.5 into KB D into T into FU. Okay, D diameter of the bolt. Okay, T thickness. Right now we don't know what are the angle thicknesses we are going to adopt. So what has been done is the gusset plate thickness has been substituted in this calculation. Okay, and FU ultimate tensile strength of the plate and the bolt material. Okay, sorry, ultimate tensile strength of this bolt. Okay, so one more factor what you have is KB, which depends on these three ratios, E by 3D naught, P by 3D naught, or FUB upon FU. Okay, out of these three, the least one we are going to take it as our KB value. So in this, what we are coming across is 0.648 is the lowest value of the KB in the three ratios. So KB is 0.648. Okay, and VDPB. Okay, design strength of the bolt under bearing, it is coming out to be 85.01 kilonewton. Okay, so it is 85.01 under bearing strength, whereas under shearing it is 28.97. So the bolt value will be 28.97 kilonewtons. This will be the strength of the bolt. Okay, so out of these three, or these two, single shear and bearing, whichever is least, that will be taken as our strength of the bolt over here. Okay, so my strength of the bolt will be 28.97. Based on this strength, I'll be deciding what number of bolts will be coming in the connection. But in any case, if the bolt is coming less than 2, we'll provide 2 numbers over there. Okay, we are not going to provide less than 2 bolts in any connection. At least we'll provide 2 bolts in the connection. Okay, so that is the connection of what we'll do. And now let us come to the first member. Okay, I'll take the member AB for the design first. Okay, so in member AB, what we are seeing is, in this member, its length is 1.73 meter and force 27.5 in compression and 24.9 in tension. Okay, so here I've taken that force. So 1.730 meters or 1730 mm is the length of this member. Okay, this is a principal rafter member. Okay, and as a trial, okay, it has been adopted that we are going to provide two ISA 60 by 60 by 5. Two ISA 60 by 60 by 5 are the members what will be provided. So how I decided these members? So on trial basis, what I'll do is I'll at least provide a member which can accommodate a bolt of 16 mm diameter. For 16 mm, 18 mm will be the bolt hole diameter. So this leg which will be connected to the gusset plate should be sufficiently wide enough so that it can accommodate 18 mm diameter bolt hole in it. Okay, so if I use 60 by 60 by 5, that will be sufficient for me. Okay, and also let us check it whether it will be sufficient to carry the force of compression or no. As a trial, it has been chosen as a trial. Okay, we can try with 45 by 5 or 45 by 8 also. Okay, once you do these trials, 1 or 2 trials for the member, for designing a truss member, you'll get an idea of how the member sizes have to be chosen over there. Okay, what you need to do is look for the connection first. Okay, one is it should be able to accommodate the bolt hole in it. The second one, later one, is the member length and what is the force in the member. Okay, that has to be given the consideration. So as a trial section, you need to decide on this basis. So if the member length is large, okay, even if the force of compression is small, you require a larger size members over there, okay, so that the KL by R ratio will come down. The larger the member size, okay, or the area of the member, radius of gyration will increase, and that will reduce the slenderness ratio of the member. KL by R will get reduced for the given effective length. When R is increased, you'll get a lower value of KL by R, and the member will become safe in compression. Okay, that is what you need to do it. Normally designers, what they look for is economy also. Okay, so they do 2 or more trials with the sections, okay, and then they will fix up one of the section. But for your purpose, since you don't have much time for doing more number of trials, what you do is you fix it on a higher side. Okay, the member what you are going to select, choose it on a higher side. But for that, you don't make that all members are of one size. Don't go for choosing 100 by 100 by 10 and provide it for all the members. That is not the design. Okay, so you have to do the design, right? If I go for choosing a member size of 100 or 150 by 150 by 10 all members will become safe. Okay, that is not correct way of doing the design, and we are not looking for such designs over here. Okay, depending on what is the length of the member, what is the force of compression in it, on that basis go for determining the member size. Okay, you just have to do some trials. Okay, once you do those practice, you'll have an idea of selecting the member size. Okay, how I can quickly choose a member size just by looking at the length and the force of compression. Okay, because this will be subjected to buckling under compression. That's why I'm talking about the length and the force of compression here. Okay, so I have done the trial, and it is not that 60 by 60 by 5 just came in my mind and I have put that. Okay, I done the trial. I have not shown them here. Okay, to reduce that rough work, I have not shown those trials here. That's all. I have shown the trial of only one, that is a trial section of 60 by 60 by 5 here. Okay, once I choose this, the area of this section is 575 square. So what you have here is, in this table, steel table, if you go to this 60 by 60 by 5, okay, so I have this 60 by 60 by 5 thickness, angle size 60 by 60. What you have? 5.75. This is the cross-sectional area of the member. Okay, so 60 by 60 by 5, 5.75 centimeter square, or in terms of square, it comes out as this into 100, 575 square. Okay, so this is what the cross-sectional area is there. In addition, you also require what is the radius of gyration. Since it is equal angle section, you'll find that Rxx and Ryy will be same, and the value here, it is 18.2 mm, 18.2 mm radius of gyration. This radius of gyration and the area, what is written here, it is for individual angle section, for one angle. Okay, ISA 60 by 60 by 5 for one angle. This is the cross sectional area, and this is the radius of gyration about x and y axis, Rxx, Ryy, horizontal axis and the vertical axis. About these two axes, these are the this is what the radius of gyration will come out to be. Okay, now when you combine these angles, okay, we are providing two angles connected back to back like this. When you combine them, there will be a change in the radius of gyration, but about which axis? Rxx will remain same. There will not be any change in this. Okay, so when you combine them, what will happen is Rxx, if you go for calculating the radius of gyration when you for the combined section, you'll find that it will become I by A, 2 times the moment of inertia. Moment of inertia will get doubled about this x-axis. Also at the same time, the area is getting doubled. So when you calculate it about x-axis, it will remain same, because the moment of inertia is not increasing by twice. Okay, so it will be same, 2 times Ixx divided by 2 times the area, its square root. That will be Rxx. Okay, so for that purpose, there will not be any change about this horizontal axis. Okay, about this xx axis, the radius of gyration will remain same as that of the single angle section. But when it is about the vertical axis, y-y axis, okay, so it is not coinciding with the centroidal axis of our compound section, okay. So for that purpose, you'll have to apply the parallel axis theorem. Here, when you combine these two angles, the CG of the compound section will pass through this CG of the individual section. Okay, there will not be any shift in the centroidal distance of single angle section and this combined double angle section. Okay, they are coming in the same line only. So there is no requirement to apply the parallel axis theorem. Ixx will simply, the moment of inertia about x-axis will simply get doubled. Okay, so the radius of gyration is not changing here. Okay, when it comes to y-y axis, this vertical axis, what is happening is there is the centroidal axis of this angle section, individual single angle section is somewhere over here. Okay, whereas the centroidal axis for both the sections considered together, this compound section, it is passing from the center, from the middle of this gusset plate. Okay, so I want to know what is the moment of inertia about this y-y axis of the two angle sections. For that, I have applied this parallel axis theorem. What will be the moment of inertia here? It will be moment of inertia about their own centroidal axis, IgG, plus area into yc square. Okay, area into yc square. That is what the parallel axis theorem states over there, or the parallel axis theorem is. So what you have is, this is the centroidal axis of the single angle section somewhere over here. I can get what is this distance CYY. In steel table, you will find it as CYY mentioned over there. Okay, so that can be obtained from the CYY. Now, this distance is my YC over here. Okay, so from here till here, this is our YC. That is YC what has been considered here. I hope you remember these relation IgG plus A into YC square. This is the parallel axis theorem. Okay, so from that parallel axis theorem, I have come across this calculation. Okay, if you remember, this was the parallel axis theorem what you have derived and used in engineering mechanics. The same has been applied. Where do you get this IgG? IgG can be obtained from the steel table. Okay, area we have taken here 575 mm square. Okay, YC we can obtain it using steel table. Okay, YC, how you calculate is the centroidal distance from this face of the angle up to here. Okay, plus half the thickness of gusset plate 10/2. Okay, so here, just a minute. I want to go to the steel table. Anyhow, so are you able to follow this or no? It may be a little bit difficult. Right. So what we have chosen is this ISA 60 by 60 by 6. Okay, I told you the cross-sectional area. So center of gravity CYY, CXX and CYY. You can see CXX and CYY. This is CYY from the face of this angle section. Okay, so what is the distance of CG? It is CYY. So that distance I can find it in this steel table. Okay, so that is one thing what is required for us. And in addition, moment of inertia is required for us. Okay, so since it is symmetric, equal angle section, IXX, IYY will be same. So this IXX and IYY have been taken from this column of moment of inertia. Okay, so what I took is Cyy and the moment of inertia for this. So Cyy, it is what? 1.65 centimeter or 16.5 mm, whereas moment of inertia is 19.2 centimeter raised to 4 or 19.2 into 10 raised to 4 mm raised to 4. Okay, so got this? These properties are available in the steel table, Cyy and moment of inertia. Okay, now with that, when I substitute them, 19.2 into 10 raised to 4, this is centroid, the moment of inertia about the centroidal axis of that angle, IgG, plus A into YC square. YC consists of two distances, one Cyy, measured from the face of this angle up to here, up to its centroid. Okay, this one, 16.5 mm, plus half the thickness of this gusset plate, because we want moment of inertia about this y axis. So YC has to be taken from this y axis. So 16.5 plus 10 by 2, that will be YC. So when I calculate that on substituting values, what I'll get is 915.5 into 10 raised to 3 is the moment of inertia. It is multiplied with 2 because two such angles are there. It is a double angle section. Two such angles are there. Okay, whatever calculation I showed here, it was for single angle. If you have two angles into 2, so that will be the contribution of two angles for the moment of inertia about y axis. Okay, so note that rxx about this horizontal axis, about this axis will remain same. No change will be there. It will be same as single angle section, whereas moment of inertia about y axis will get changed. Now what is the value of ryy for the combined angle, double angle section? It is 28.2 mm. Earlier rxx ryy were same, 18.2. Now which is the least radius of gyration now? For this double angle section, what is the least radius of gyration? rxx is 18.2, whereas ryy is 28.2. So the least radius of gyration, what we come across is rxx, about this xx axis, 18.2. So if at all, if this member buckles, okay, this principal rafter member, what member we are considered here, member EB. If at all, if it buckles, then it will be buckling about xx axis. Okay, it will be bending or buckling about this xx axis, because radius of a gyration is less about this axis. Okay, so we have to consider this as our this one, the critical radius of gyration, and from this we'll calculate the slenderness ratio. So the minimum radius of gyration is rxx, which is 18.2. Okay, so this is the calculation of the property of that member. Any doubt in this part?
No, sir.
You have to concentrate a little bit. Some basic concepts will come over here. Calculation of radius of gyration, okay, moment of inertia, these terms are coming here. So you need to understand them, how that calculation will be. Okay.
Sir,
Yes.
sir, how to search
What?
in steel table, sir?
Steel table, you will get the columns. You have the columns over there. So this is the steel table. I'll just zoom out. Values, you don't worry. You just see in this, I have zoomed out. So here it is taken here. Okay. So what I have taken, angle section, ISA 60 by 60 by 5. So I've chosen this particular angle section over here. Okay. So this is the steel table, what you have. So in this steel table, what you
Sir,
get
it is not
is,
visible.
wait, which is not visible? What I'm doing right now?
Steel table. Steel table.
It may come up. For all, it is not visible. Anybody who can see the steel table?
No, sir.
Sir.
No, sir.
Just a minute, just a minute. Okay. Now it is visible.
Yes, sir.
Earlier
Yes,
PPT
sir.
was visible or no?
Yes,
It is
sir.
visible, sir.
Visible, sir.
Okay, okay. So what I have here is in the steel table, this is our ISA 60 by 60 by 5, right? Okay, this is the angle what we have adopted here. And for getting the properties, what properties are required is, one is this cross-sectional area, okay, so 5.75 centimeter square, okay, that was required for us, or 575 square. In addition to this, the center of gravity, position of center of gravity with respect to the angle section was required. So the CXX and CYY, it is 1.65 centimeter or 16.5 Then the moment of inertia, Ixx and Iyy value. Okay, since it is equal angle section, both are same. It is mentioned Ixx equal to Iyy. How much it is? It is 19.2. Okay, now it is clear. This is how
Yes, sir.
I have chosen the properties of this section. One, area, this is here, okay, and then the this one, centroidal distance from the angle, okay, so that is one, and one more is moment of inertia. Okay, so these three properties I have taken. Okay, if you refer to the steel table, you go with this columns and the section what we have adopted. From there, you can determine those properties. Right? Is that clear about the properties? Any other doubt in that?
No, sir.
Fine. Okay. So up till this part, anything else in this? We started with those calculation of the connection details, pitch distance, end distance, edge distance, okay, with the given bolt diameter. Then what we did was we went for calculating the strength of the bolt, okay. So as we do for normal black bolts, it was mentioned 4.6 grade, means it is a ordinary black bolt. So for that, I've done the calculation of bolt strength calculation. It is calculated in single shear and double shear as well as in bearing, and the least of these will be taken as our strength of the bolt, okay. And coming to the member design, so a suitable member section has been chosen here by trial. It is purely by trial, okay. So for this member section, what we need to check is what is the least radius of gyration, okay. So you need to apply the knowledge of mechanics here, okay, Rxx and Ryy, check which one will be least, okay. So we concluded that the minimum radius of gyration is Rxx, okay. On calculation and comparison, it came to our this one view that radius of gyration, least radius of gyration is Rxx, okay. So now we'll proceed with the design part of this member. So taking this least radius of gyration, you need to find out what is the uh, slenderness ratio, okay. So effective length, I have taken 0.8 times the unsupported length here, okay. Even if you take this 1730 also fine, it is a center to center distance between the connections, okay. So don't worry about this factor what I have considered. I have taken 0.8, and this can be between 0.7 to 0.85, okay. So you can adopt between this, that is the one guideline you can take, okay, if you don't want to consider the entire hinge connection at the ends, okay. So you can adopt between 0.7 and 0.85. Average value of 0.8 is fine, okay. So effective length, what it comes out, 0.8 into 1730, okay, it is 1384 right. Now this is by using the formula. What formula is there in the code? On that basis, FCD is calculated here. So this FCD comes out as how much? So this FCD calculation will require you to calculate lambda and phi, okay. And the imperfection factor, it belongs to class C, or the value of alpha is 0.49 in that case, okay. So from this IS 800 table, you will get it 0.49, Is that okay if I skip that equation part? If you have any doubt, please ask me, because this particular part I had gone through that yesterday. This is totally from the IS 800. Okay, so effective length, from effective length, what is the permissible stress in compression has to be determined. Okay, for that lambda and phi, you require the lambda and phi values. Okay, that calculation, if you are doing it by using the equation, that should be done. Or else you can, what you can do is go for table 8C and 9C. Okay, from there also you can obtain the value of these stress reduction factors chi, or directly FCD value itself. That can be done. If not, let me just take this over here. Okay, so lambda, what you have is root of Fi by FCC. So this is the formula in section 7 of IS 800. So FCD, Fi upon gamma m naught divided by phi plus phi square minus lambda square, this raised to 0.5. Okay, and it has to be less than Fi upon gamma m naught. That is the limit. Okay, now how do you calculate this phi and lambda? For that, you need to first calculate this FCC, pi square E divided by KL by R. In our problem, this R, what you will consider is RXX, the least radius of gyration. Is it visible if I am switching like this? Now I am in PPT.
Yes, sir.
Okay. So here lambda is calculated Fy by FCC. What is FCC for us? Pi square E divided by KL by RXX. Okay. KL, it is 1384. So pi square into 2 into 10 raised to 5. This is Young's modulus for steel, divided by this KL 1384 divided by 18.2, which we came across here, 18.2. Okay, 1384 divided by 18.2 the whole square. So this will give you
It is showing code
FCC.
book.
So not visible, sir.
Okay.
Sir, screen is not visible.
Yes, it is. Yesterday that problem was not there, no? I think when I switched from this one to other, it was coming out. Okay, let me be in the presentation only. Any of the formulas are written here, and refer to the IS 800. All these things clause I have mentioned here. So I've taken all this formula from this clause. I will not switch to that code book again. So lambda, okay, root of Fi by FCC. So FCC, irregular buckling stress, it is over here. What values we get, K, L, and R minimum, what we obtain. So on substituting them in this equation, we have the FCC values 341.35 Newton per mm square. Okay, so what we have from this lambda, it is root of 250 by 341.35. So lambda is coming out to be 0.855. Okay, for us lambda is 0.855. Now using this lambda, okay, what is the value of phi? Phi is 0.5 into this 1 plus alpha into lambda minus 0.2 plus lambda square. Okay, so lambda we have already calculated. Alpha, what I told you, angle section, they belong to buckling class C, for which the imperfection factor value is 0.49. The table is available in IS 800, table number 7. From there you will get it 0.49. Okay, it will remain 0.49 only as long as you are using the angle section. Okay, now what about our phi value? Okay, if I substitute these lambda and alpha values in this and calculate, phi comes out to be 1.02. Okay, that is the value of phi. So on getting phi and lambda, now we can go with this calculation of the permissible stress in compression, FCD. Okay, that is 250 upon gamma m naught, 250 by 1.1 divided by 5 plus pi square minus lambda square raised to zero point 0.5. This expression, what I showed you over here at the beginning, this has been used and the values for phi and lambda are substituted in this. So FCD, how much it is? 144.18 Newton per mm square. From this calculation, it is 144.18 Newton per mm square. Okay, what is the allowable FCD? Fy by gamma m naught. It cannot exceed your yield stress, factored yield stress. So factored yield stress is Fy by gamma m naught, and that is 227.2 Newton per mm square. So fine, our FCD, what we calculated, it is less than permissible yield stress, 227. So you will be using this value for calculating the strength of member under compression. So AE into FCD, that is the strength in compression, PD. What is AE? Two angles are there. Area of each angle is 575 mm square. So AE 2 into 575 into our FCD, what has been calculated, 144.18. So this gives us the strength in compression as 165.8 kilonewtons. Okay, whereas the force of compression which was there in that member, it was 27.5 kilonewtons. So it is safe. What section we have chosen, it is capable of withstanding a force in compression of 165.8 kilonewton, whereas the force to which it is subjected is 27.5 kilonewton. So it is safe. It is high on a higher side only if you observe these values. Okay, it is much more higher than what is required. But for connection also, as I told you, we require those sizes of the legs of the angle. So this is one part of the design of that truss member. We have designed it for the compression. Now what we are going to do is, we'll check it for the tension, whether it is safe under tension or no. So normally what happens is, if the member is satisfying compression requirements, it will be safe in tension as long as the forces they are comparable. Okay, they are not there's not much difference. If there's not much difference in force of compression and tension, so normally it will be safe, but you have to check it. Okay, so what you have to check in for tension is, one is yielding of cross section, whether the cross section is safe against yielding or no. So here you have TDG, which is given by AG into Fi upon gamma m naught. This is in the clause 6.2 of IS 800. Okay, so what I have, gross area, it is 2 into 575, and yield stress is 250. Fe410 grade of steel, the yield stress will be 250 Newton per mm square. So Ag into Fi upon gamma m naught. Okay, so that comes out to be 261.36. Okay, this is one of the strength in tension. Don't compare this with the force which is given to us right now. Okay, don't compare this, because we have to decide what is the strength of the member in tension. Still, we have calculated one of the criteria. We have determined against yield criteria. Now one more criteria is rupture. Okay, now coming to rupture, you have this calculation of the area, TDN. Okay, so considering the shear lag effect, it is given as 0.9 ANC into Fy upon gamma m1, sorry, 0.9 ANC into Fu upon gamma m1 plus beta into Ag naught into Fi upon gamma m naught. Okay, the equations are taken from clause 6.3 of IS 800. Okay, I'll give you this PPT. This reference will be mentioned over there. Okay, you can go to that clause and check this equation. Okay, all these are from IS 800 and steel table, values from steel table only. So now, number of bolts required in this connection. What is the number of bolts required? Since it was a double angle section, I showed you here, it is double angle section. Whatever bolts you place over here, they are subjected to double shear. So strength under double shear and bearing, out of these two, whichever least is considered here. So it is 57.94. This was the strength in double shear, what we have seen earlier. Okay, so what number of bolts are required? Whatever the factored force is there in the member divided by strength of the bolt. Okay, factor force in the member is this 27.5 kilonewton, and the bolt value is 57.94. So we require not even one bolt, but what we have decided is to provide at least two bolts. So for that purpose, two bolts have been used in this connection. We have provided two bolts with a pitch of 50 mm and the edge distance of 35 mm. Okay. Now with this two bolts, what will be the value of beta? So beta will be this 1.4 minus 0.076 W, this width of the outstanding leg 60 mm divided by thickness of angle 5 mm into Fi 250 divided by Fu 410 into Bs by Lc. Okay, Bs here 60 plus up to the center of this connection 25 minus the angle thickness 5. So Bs comes out to be 80 mm. Okay, end connection length, what we have, only one pitch distance, because we are providing two boards. In between those two boards you have come across only one pitch distance. So Bs upon Lc 80 by 50. 50 is this pitch distance, right? So what is the value here? I'm getting it as 0.51, but we have upper limit and lower limit over here. Okay, so it is below lower limit, so what I'll adopt is beta as 0.7. Okay, the minimum value of beta, so that has been taken here. So on this, what will be the strength? So ANC, what you have, ANC has to be calculated considering the bolt holes, deduction for bolt holes. So 60 is the width of this leg, okay, minus half the thickness on this junction, minus the bolt hole diameter. 16 plus 2, 18 mm is the bolt hole diameter. So this entire thing multiplied by angle thickness will be your ANC, net area of the connected leg, which is 197.5 mm square, right? And this has been substituted here, 0.9 times ANC into Fu upon gamma M1. Okay, then beta B into Ag naught into Fi upon gamma M naught. How Ag naught is calculated? Simply length of this unconnected leg minus half the thickness of the angle section at this junction into the thickness 60 minus 5 by 2 into 5, 287.5 mm square. So this will be Ag naught into Fi upon gamma m naught. Okay, so altogether TDN, it is 104.04 kilonewton. Okay, this is second strength in tension, considering the criteria, one more criteria, which is rupture at critical section. Okay, so that is one. And one more, what you have to do is calculate strength based on the block shear. So at the end connection with the gusset plate, this is what you have. We have two bolts here, one and two bolt. The edge distance is maintained here, 35 mm. This is the end distance maintained, 35 mm, same. Okay. In between these two bolts, the distance is pitch distance 50 mm. Okay. And 1, 2, this line 1, 2 is our shearing plane. 2, 3 is our tension plane. Okay, so what is the net area along the shearing plane and the gross area along the shearing plane? Net area along the tension plane and gross area along the tension plane. So here you have gross area along shearing plane, length of this line 35 plus 50. Okay, so the 35 plus 50 into 5 mm angle thickness. So this is our gross area along shearing plane. Net area along shearing plane, in that calculation, what I will do, I'll deduct for these bolt holes 1 plus half bolt hole here, 1.5 bolt holes. So 35, okay, this 35 plus 50, this distance, in that minus 1.5 into 18. Bolt hole diameter is 18 mm, and 1.5 such bolt holes are coming in this line along 1, 2. So that deduction has been done. After doing that, into thickness of angle. So it will give you the area. Okay, this area, what I am talking, they are perpendicular to our screen. Okay, they are perpendicular to our screen, right? So these are the areas along shearing plane, net gross area and net area. Along the tension plane, what I have length is this 35 mm. So if I want the gross area, simply this 35 by 5 gross area. When I am calculating the net area, 35 minus half the bolt diameter, this bolt diameter. So 35 minus 0.5 into 18 into 5 mm angle thickness. Okay, this is 130 mm square. So these two equations are there for calculating strength in block shear. TDB1 and TDB2. I have called them TDB1 and TDB2 in clause 6.4. They are not mentioned it as TDB1 and TDB2. Simply they have called it as TDB. But you have to substitute accordingly the gross and net area in these two equations and come up with strength in block shear. So what I get is one of the strength in block shear is 96.86 and one more is 95.03 here. So out of these two, the lowest is 95.03. So this will be considered as the design strength in block shear. And when I compare block shear strength, rupture strength, and strength in yielding, out of these three, what we have, the least is this 95.03. So strength under tension, design strength under tension is 95.03. And but still it is more than our uh, tension to which this member is subjected. Okay, so here this is into 2 because of two angles. TD, total strength under tension, it is 2 into 95.03, which is 190, and see that it is more than whatever the force is coming in this member, 24.9 kilonewton. Okay, so this member, what we have decided, 60 by 60 by 5 for the principal rafter, it is safe. I can provide this angle section of 60 by 60 by 5 for this member AB, which is of 1.73 kilometer length. And these are the forces. We have checked for these forces, designed for these forces, and we have made sure that it is safe under these forces. Okay, so this one member design, what we have done, this is over. Now similarly, what we have to do is go for the next member. We'll have to take up the next members and design them for one of the force and check it for the other force. Okay, so please go through this. What I have explained today, you go through this one of the member. Okay, tomorrow we'll continue this. Okay, and then I'll give you one problem. Once we complete that entire truss, we'll go through other member designs and check, see the design, and later you can go for practicing problem. Okay, so
Okay, sir.
this we'll stop it here. We'll join, I think, on Monday class is there. Next class we'll come across Monday. Okay, fine. Thank you. In the group, the PPT will be shared later, not now. I'll finish the class on Monday and share it later.